And yesterday I said something about algebraizable formal schemes, and I said I gave as a definition a formal scheme X is algebraizable if there exists a scheme X and a subscheme Y such that this is isomorphic to X, Y. And as Stefan made me observe, there are other problems and one of the problems in formal geometry is to give criteria to obtain that a formal scheme is algebraizable, and it happens that actually we have essentially no criteria to establish this. There are very few. Another problem of algebraization, which actually will be the one which is will be attacked by Jean-Benoit next week, I think, is the following. It is something in between this. Suppose that you are in this situation. So suppose that you have this formal scheme, and inside here you have a formal scheme. So this is a formal scheme inside a, let me call it, algebraic formal scheme. And the question of algebraization, when can we find a scheme? Let me call this Z, a scheme, Z, closed scheme, a closed Z inside X and Y, Z, X, such that Z is Z, Y. So this is okay. This is another kind of problem which is also called an algebraization problem, and let's say that the situation is the following. Here essentially we have no tools to attack this problem. I will state the only tool we know about this, which is a theorem by Grothendieck actually. Here there are more tools, and they will be studied in some cases, some interesting cases by Jean-Benoit next week, and there is a nice theory behind this, but there are still many open problems here. And just to give again an example of yesterday, that if you take X, Y to be A2 localized at the origin, and then here you can take the closed formal scheme given by the ideal given by y equal to sum of x to the power n to n factorial minus. And so, as I said, this is actually isomorphic to A1 abstractly, as an abstract formal scheme is isomorphic to this scheme, to this formal scheme, and as so this, if you see it as an abstract formal scheme, is algebraizable. But if you see it as a formal scheme inside this formal scheme, you cannot solve this problem. You cannot find a subscheme of A2 such that this is the completion of it. And so this is the way to say that this is, and you see, this is the solution of a differential equation. And usually the problem is given a solution of a differential equation or a leaf of a foliation, can you know the leaf of the foliation do not exist in the algebraic category, but at least it is often exists in the formal category, and you want to know if can be algebraized, if the solution is algebraic. Okay. So I would like, since yesterday I talked actually I'm late, I would like to start by stating the Grothendieck theorem, and then I will try to see how much I can explain about tools of the proof. So the Grothendieck theorem, as I said, is the only, to my knowledge, the only case where we can attack this kind of problem. And the situation is the following. So let's say Grothendieck algébrisation theorem. So I start with a ring A, which is complete with respect to some ideal. And I can look to a scheme so no, I will state directly the theorem by Grothendieck. Then I can look to this formal spectrum of A, which is a formal scheme with a map to here. And I suppose that I have a formal scheme like this, which let me such that the ideal that f minus 1 of I is an ideal of definition of X. So in particular, I suppose that the morphism F is proper. And there exists a line bundle L on X with the property. So I recall that I have this following diagram, and this is the support of my formal scheme, is the underlying space, the underlying topological space, which is a scheme. I suppose that this morphism is proper, so this morphism is proper, and I suppose, let's call it this I0, such that I0 upper star of L it will be a line bundle here, is ample. Okay? So this is the hypothesis. So in particular, this implies that X0 is projective over spec of A divided by I, and the theorem seems that this is the statement. Let me see if I am forgetting some hypothesis. Yeah. Suppose that this is the situation, then X is algebraizable. Which means that I can put here a scheme such that this diagram is Cartesian and this is proper, projective actually. And so to my knowledge, this is the only theorem we have to attack this situation. And actually, it is very powerful and very useful. No. So I learned that in my experience that when you are late in your lecture, you have to start from the end. So you finish every time. You do whatever you can do, and at least you stated what you wanted. Okay, so I will try to give some steps of the proof, but putting difficulties always in the late. So one thing that I would like to remark is that a typical application of this theorem is, this I will just say a few words, is in deformation theory. In deformation theory, we have the following statement. You have the following problem. You have, let's say, a complete ring, let's say local ring, a complete local ring, and you have, so you have the ideal, let's say the ideal is M, and and you have K is A divided by M. So you have the following situation. You have spec K inside spec A, and then you suppose that you have a variety here, a smooth projective variety here. A projective variety here. And deformation theory says, can we put a scheme here in order to obtain a Cartesian diagram, which means essentially that you can deform x0 over a bigger ring instead than your field. Yeah, sorry. Can you put a scheme here in order to obtain this? So what you have usually, that you have spec of A divided by M to the power n to spec, and here you have spec K, and then x0, and the first things you can try to do is, let's say, try to deform, not on over A, but to deform the problem over this ring, which is just topologically is exactly this, but it has an nilpotent structure. And so suppose that you can do it. And if you can do it, if you can deform x0 to xn for every n, you are building a formal scheme x over spec formal of A spec K0 X0 like this. And in order to solve this problem, you have to deal with some deformation theory over Artinian ring. There is a very well developed theory on that. But at the end, you reach a formal scheme, which is not a scheme, not the solution of your problem. If you can deform a line bundle, ample to an ample line bundle L0 on X0 to a line bundle L on X. So you have to deal with a deforming line scheme and line bundle. If you can do it, and actually in many cases, for instance for curves, you can do it, then you can apply Grothendieck's theorem. Then Grothendieck's theorem tells us that we can find the X.
Suffices to the form L to every xn.
Sorry?
It is sufficient to the form L to every xn or no? As an ample line bundle.
Yes, yes, yes. I will come to that in a moment.
Don't you have to assume that the L that you construct is ample? It's ample on X0?
Ample line bundle L0.
One ample
L.
Yeah, no, look. There is a line bundle L such that the restriction to the
Only the restriction.
yeah. If you think a little bit, yes. Yeah. This is the main part of the theorem of growth.
Does openness or ampleness also is formal set?
Sorry?
I mean, it's an equivalent question. Does openness or ampleness?
Yes, yes. Essentially, this is the point. But the point is okay. Here we are going inside the proof. Essentially, it happens that let me answer late to this kind of questions because it is exactly the key of the point of the proof of Grothendieck. So this is let's say that the Grothendieck algébrisation problem theorem is a key point in the theory of deformation. So, but it is interesting in its own, and it can be applied, and as you can imagine, it's a theorem by Grothendieck, so it can be applied in very general situations, characteristic P, characteristic 0, even when the ideal is not principal, and many situations. And but it is important to notice that here there is in the bottom line there are formal completion of rings. So there are formal affine schemes, not arbitrary schemes. And if I have time, I don't think so, but you can have counterexamples to this statement if the bottom line is not an affine scheme, but just a scheme where you complete. In principle, you can write the same diagram where the bottom line you complete a scheme, and then on the top you do the same. Okay, So this was just to explain why this theorem can be interesting. So first of all, I would like to answer to Francesco's question. So what is a sheaf, a coherent sheaf on a formal scheme F is give rise, so we have your formal scheme, and then give rise to, call this IN, coherent sheaves on Xn simply by taking I up a star of F, okay, which I will call it Fn. So you have this formal scheme, these sheaves, and you restrict to each of the Xn, and you will obtain a sequence of formal of coherent sheaves. And actually, you can reverse the situation. I also have some maps Xn included inside Xn plus 1 and call it this Jn. So suppose yeah. Suppose we have a coherent sheaf Fn on Xn for every n, and exact sequence E n times Fn wow, okay, Jn minus 1 lower star of E n minus 1 so you see, I'm just saying that I'm taking a coherent sheaf on each of the Xn, which are giving a projective system, and I can consider the limit of Fn by this map, and this will give rise to a coherent sheaf on X. So you see, given a coherent sheaf on X, I get sheaves on Fn, and actually you can see that here, even here, F will be the limit on the Fn. And conversely, given sheaves on each of the Xn, you will build up a sheaf on X. Okay, so this, I think, answered to your question.
Is it clear that this curly F is still of finite presentation?
This must be proved.
Must be proven. Not,
This is called, again, Artin-Ries theorem. So Grothendieck's theorem, as you can imagine in Grothendieck, is an equivalence of two categories. So Grothendieck start from the situation where you have x over spec A, spec formal of A, x, this, and here you have a map Ix. And you have a map Ix up star, and you suppose that F, let's say, is proper. But okay, this is where Grothendieck proved the theorem, which is quite hard. And you have this map with this functor from coherent of x to coherent of curly x. Okay? And it happens that this functor, we already know that is exact, because I said you yesterday that this morphism is flat. But actually, Grothendieck proves that it is an equivalence of categories. Okay. And I will come to the proof, or I will sketch the tools of the proof of this, but I will just to apply this for the moment. But this is the key step. This is the key step. This is the key step, and this can be seen more or less as what is called the formal gaga. In particular, be careful to beat this hypothesis. In particular, if too late Z is a sub-scheme, is a subformal scheme if you have this, you can look to the ideal of Z, the ideal sheaf of Z. It is coherent. So there exists an ideal sheaf inside OX which corresponds to it because it is an equivalence of categories, which implies, with not so much work, that Z is, let's say, the completion of the scheme associate V of. Okay? Essentially, this equivalence of categories tells you that there is also an equivalence between subschemes, subformal schemes of it, and subschemes of X, because you just take the ideal. This ideal sheaf corresponds to an ideal sheaf inside OX. So there is a scheme, a closed subscheme of X associated to this, which is just that. And then you can check easily that under this condition, the completion, if you take the completion of Z with respect to the ideals corresponding, coming from A, gives you the formal scheme you started with.
Is that what it means to be algebraic?
Yes, this is what yes, this means that is algebraic. So, yes, in this situation. Why it is was this was written at the beginning. I had an ideal divided by M, and here I take F minus 1 of M. Is okay. This is a special situation. It's not. It's something like horizontal, vertical situation. I take some way. I take. If you think this as a local ring, I take the special fiber, which is a closed set, and I take the formal completion of it. Okay? So this tells us that if we are under this situation, every closed subscheme here is algebraizable. Aha, this is a good question. So the point is that the proof is much easier in the case of projective, but Grothendieck was able to do it in proper case. But there's a lot of work more. And so you are in this situation, and actually and now I would like to explain the proof of that. In the proof of that, with a little bit of work, so proof of Grothendieck, how you call it, algébrisation. Essentially, you prove that you can take L, I, 0 up a star of L, can give rise to embedding that you take a power of it, of x0 inside P of, or inside some Pn of A over M. And a little bit of work you will show that I up a star of n of L give rise to an embedding of xn inside the same Pn, but this time A to M n, and in a coherent way. In some way, you prove that the line bundles are giving a coherent linear system, which then you do it for every n, which will gives you an embedding of this inside the completion of Pn over a spec formal of A. Okay? Because at the limit is this. And now you apply this, and you obtain that X must be algebraic. So you see the similarity. This is like Chow theorem. In some way, the existence of an ample line bundle tells you that a subformal scheme of the projective space is actually algebraic under this situation. Under this situation, a subformal scheme of a formal scheme of the projective space is algebraic. So this theorem is like this, actually. This, better. This is essentially a strong version of Chow theorem in this situation. Okay?
So you are assuming that this deformation of L is ample to every step.
Yeah, but the point is exactly this. I didn't give details, but the fact that is ample on the special fiber may induce that is ample at every step. Yeah, because you can deform it. I mean, you have L, which is given on the formal scheme, and which is ample at this first step. It's Nakayama lemma. It's not more than Nakayama lemma. Is ample at step 0, then it becomes ample to every step, and even in a coherent way. So it's like you say that ampleness if it's ample on the special fiber, it must be ample on the generic. Here there's no generic fiber, but
so why does it stay in the same dimension?
this is part of the proof. Part of the proof is to prove that each time you can, that as soon as this is in some way you prove that the space of section is essentially the same because of, I mean, there are a lot of things to do. You use this fact. You use this fact, and you also use typically this fact, that you have Ln minus 1, and here you are going to find something like L0 tensor n divided by n minus 1. This is something which is supported on the special fiber. minus 1, yeah. Thank you. And now you can this suppose to simplify that M is principal. To simplify, otherwise you have a small complication. So essentially, this is isomorphic to OX0. So this gives you H naught of xn ln to H naught xn minus 1 ln minus 1, and then you have H1 x0 L0. And then you can suppose that this is 0 because it's ample. Because it's ample, so you see that you can deform all the global section. You see, you add the sub-global section here, you can deform them. And that means that you can deform tilde to the formal limit. But anyway, you take simply a subspace of the right dimension.
Yes, but if you project, maybe it's not an embedding anymore.
No, because you project, you obtain exactly the same. Okay. So you see, essentially, this exact sequence tells you that okay, I didn't state one thing which is called the theorem of formal function, but anyway, this will tells you that you have using this exact sequence, you obtain that you have this. You have this exact sequence. That means that here I can take let's say a modular, a vector space inside here, which dominate, which will gives you a line, which will gives you a linear system, so a map in the projective space, and then you obtain this. There is some work, but it works in some way. Okay. So you can imagine that this is much deeper than that. That is a corollary. Oh. So now we come to some ideas. As you see today, they were just ideas. Some ideas how to prove this statement. So the first thing, one prove that I upper star is fully faithful. Which means that if you have two, yes, f g to I up a star of f, I up a star of g is an isomorphism. And here we are using the fact that A is complete and is affine, because we actually this is a coherent module on spec A, because the morpheme is proper. Here we are using properness. And so, if M is a coherent, so it is, in particular, it is a finitely generated A module. But now, if I said you to yesterday, if M is a finitely generated A module, the completion of M is just M tensor A hat. Okay? But if A is equal to A hat, that means that M is already complete. Which, if you interpreted the completion, if you take a module here, this is the completion. The pullback JA up a star of M is just M hat. This you can check by construction. Actually, there is a theorem against, but anyways, this is the case. So that means that exactly this is this, because we are using coherence and we are using properness. So as soon as you cut one of these two hypotheses, you cannot, coherence will tell you that this is a finite type. No, properness will tell you that this is a finite type, and then we are using the fact that A is affine to use this property. Otherwise, if A wasn't affine, you cannot say this. And now I make a restrictive hypothesis, because otherwise it is much harder. I will suppose that F is projective. So I have an ample line bundle. Okay? So I have an ample line bundle. And what is the key proof, which requires a bit of work, is the following theorem. Is let G be a coherent sheaf on X. Oh, be careful. Since we know that the thing is flat and we have this property, we just need to prove these properties. You know, fully faithful means injective between categories. So we have to prove that this function is surjective. Surjective means that you have to prove that given a coherent sheaf on curly x, there is a coherent sheaf on x such that, so this is the aim. So this is what I'm trying to do. I started with this, and then the theorem say there exists A such that G of A is generated by global section, which means that I have a vector, a module V on a module of finite type, and a map from V tensor OX to G of A, which is surjective. So, and again, as I said, I'm pushing always back the key point. This is the key point of the key point. It's the key of the key. Because once I prove this, I finish. Once I prove this, I finish, because that means I can look to the kernel, K, the kernel of, so I have a map from V of minus A over G, which is surjective. So I can look to the kernel, and I apply the theorem again, and I have an exact sequence W of minus B, V of minus A, G 0. I am applying the theorem again to K, okay? K will be a coherent sheaf, so I can apply the theorem. So I have a map here, which I will call it psi, but psi tilde, but this is a map of two objects which come from X. Okay, this is a coherent sheaf on X, and this is a coherent sheaf of X. So psi tilde is I up a star of some psi because of this. And so I will put G will be I up a star of cokernel of psi. And so I proved that G is the pullback of a coherent sheaf on X. "35 seconds to say how to prove this. And actually, it is similar to what was written there. You start with the restriction of G to x0. And since x0 is projective, you can find such a surjection over x0. Okay? And now you do it coherently on xn for every n, using argument of this kind, using a vanishing of cohomology of this kind. And then you find that you can find such a v which works for every, and such a which works for every n. And then this implies that it works for the formal scheme, for a theorem of formal function. And it requires a bit of work, but it can be done. Okay, thank you.